Data preparation may be one of the most difficult steps in the machine learning process. The reason is that each dataset is different and highly specific to your project. Nevertheless, there are enough commonalities across predictive modeling projects that we can define a loose sequence of steps and subtasks that you're likely to perform. This process provides context in which we can consider data preparation required for the project, informed by both the definition of the project performed before data preparation and the evaluation of the machine learning models performed afterwards. Each machine learning project is different because the specific data at the core of the project is different. You may be the first person, ever, to work on a specific modeling problem. That doesn't mean that others haven't worked on similar predictive tasks, or perhaps even the same high-level task. But you may be the first to use the specific data you have collected. This makes each machine learning project unique. No one can tell you what the best results are going to be, or what models to achieve them with. You must establish a baseline of performance as the point of reference to compare all your models, and then you must discover what models to use for a specific data set. Now, you're not alone. The vast literature on applied machine learning that has come before you can inform you as to the techniques to use to robustly evaluate your models and algorithms. Even though your project is unique, the steps on the path to a good or even the best results are generally the same for every project. This is sometimes referred to as the applied machine learning process, the data science process, or by an older name as knowledge discovery databases. This process of applied machine learning consists of a sequence of steps, which we're going to walk through in detail in the next lesson. All right, let's take a look at the machine learning pipeline, or the machine learning process. The process of applied machine learning is a sequence of steps. The steps are the same, but the names of the steps and the tasks performed may differ from description to description. Further, the steps are written sequentially, but we're going to jump back and forth between the steps for any given project. So at a high level, the process has 4 core steps. Number 1, you define the problem. Number 2, prepare the data. Number 3, you evaluate the model. And number 4, you finalize that model. Let's go ahead and take a look at these a little more granularly. Number 1, define the problem. This step is concerned with learning enough about the project to select the framing or framings of the prediction task. For example, is it a classification or regression problem, or some other higher order problem type? It involves collecting the data that's believed to be useful in making the prediction and clearly defining the form of the prediction it's going to take. It may also involve talking to project stakeholders and other people with deep expertise in the domain. This step also involves taking a close look at the data, as well as perhaps exploring the data using summary statistics and data visualizations. Step 2 is data preparation. This step is concerned with transforming the raw data into a form that's best used for modeling. We're going to dive into this step in the next session. This step is concerned with evaluating machine learning models on your dataset. It requires that you design a robust test harness used to evaluate your models so that the results you can get can be trusted and used to select among the models you have evaluated. This involves tasks such as selecting the best performance metrics for evaluating the skill of the model, establishing a baseline or a floor in the performance to which all model evaluations can be compared, and a resampling technique for splitting the data into training and testing sets to simulate how the model will be used. For quick and dirty estimates of model performance, or for very large data sets, a single train test split of the data may be performed. Now, it is more common to use the gold standard, which is called k-fold cross-validation, as the data resampling technique, often with repeats of the process to improve the robustness of the results. This step also involves tasks for getting the most out of the well-performing models, such as hyperparameter tuning and ensemble of models. Lastly, in step 4, finalizing the model. This step is concerned with selecting and using a final model. Once a suite of models has been evaluated, you must choose a model that represents a solution to your project. This is called model selection and may involve further evaluation of the candidate models on a holdout validation dataset, or selection via other project criteria, such as model complexity. It may also involve summarizing the performance of the model in a standard way for project stakeholders, which is an important step. Lastly, there will be tasks related to the productionizing of the model, such as integrating it into a software project or a production system, and designing monitoring and maintenance schedules for that model. All right, now that you're familiar with the process of applied machine learning and where data preparation fits into the process, let's take a closer look at the types of tasks that may be performed. In this lesson, let's answer the question, what is data preparation? On a predictive modeling project, such as classification or regression, raw data typically cannot be used directly. There are reasons for this. For example, Machine learning models require their data to be numbers. Some machine learning models impose requirements on the data. Statistical noise and errors in the data may need to be corrected. Complex nonlinear relationships may be used to tease out the data. Therefore, the raw data must be preprocessed prior to being used to fit and evaluate a machine learning model. This step in the predictive modeling project is referred to as data preparation, although it goes by many other names such as data wrangling, data cleansing, data preprocessing, and feature engineering. Some of these names may be a better fit for subtasks for the broader data preparation process. We can define data preparation as the transformation of raw data into a form that makes it more suitable for modeling. This is highly specific to your data, to the goals of your project, and to the algorithms that are going to be used to model your data. We're going to talk more about these relationships as we move through the course. Nevertheless, there are common or standard tasks that you may use or explore during the data preparation step in the machine learning project. A few include data cleaning, which is identifying and correcting mistakes or errors in the data. And then there's feature selection, identifying those input variables that are most relevant to the task. Then there are data transforms, changing the scale or distribution of the variables. Then there's feature engineering, deriving new variables from available data. And then lastly, there's dimensionality reduction, and this is creating compact projections of the data. Each of these tasks is a whole field of study with specialized models. We're going to take a closer look at these in Section 3. Data preparation is not performed blindly. In some cases, variables may be encoded or transformed before we can apply a machine learning algorithm to them, such as converting strings to numbers. In other cases, it is less clear. For example, scaling a variable may or may not be useful to the model. It can feel overwhelming given the large number of methods, each of which may have their own configuration and requirements. Nevertheless, the machine learning process steps before and after data preparation can help to inform you on what techniques to consider. All right, in this lesson, let's answer the question, how do we choose our data preparation techniques? As with many other questions of statistics, the answer to which feature engineering methods are best is that it depends. Specifically, it depends on the model being used and the true relationship with the outcomes. On the surface, this seems like a challenging question, but if we look at data preparation in context of the entire project, it becomes a little more straightforward. The steps in a predictive modeling project before and after data preparation inform us of the data preparation that will be required. The step before data preparation involves defining the problem. As part of defining the problem, many of the subtasks may be gather data from the domain problem, discuss the project with subject matter experts, select those variables to be used as inputs and outputs for a predictive model, review the data that's been collected, and then summarize the collected data using statistics. Lastly, visualize that collected data using plots and charts. Information known about the data can be used in selecting and configuring data preparation methods. For example, plots of data may help identify whether a variable has an outlier value or not. This can help in the data cleansing process. It may also provide insight into the probability distribution that underlies the data. This may help determine whether data transforms that change a variable's probability distribution would be appropriate. Statistical methods, such as descriptive statistics, can be used to determine whether scaling operations might be required. Statistical hypothesis tests can be used to determine whether a variable matches a given probability distribution. All right, what is data in machine learning? Predictive modeling projects involve learning from data. Data refers to examples or cases from the domain that characterize the problem you want to solve. In supervised learning, data is composed of examples where each example is an input element that will be provided to a model and an output or target element that the model is expected to predict. Classification is an example of a supervised machine learning problem where the target is labeled, and regression is an example of a supervised machine learning problem where the target is a number. The input data may have many forms, such as an image, time series, text, video, and so on. The most common type of input data is typically referred to as tabular data or structured data. This is the data you might see in a spreadsheet, in a database, or a comma-separated values document called a CSV file. This is the type of data we're going to focus on. Think of a large table of data. In linear algebra, we refer to this table data as a matrix. The table is composed of rows and columns. A row represents one example from the problem domain. It may be referred to as an example, an instance, or a case. A column represents the properties observed about the example and may be referred to as a variable, a feature, or an attribute. So a row is a single example from the domain, often called an instance. Example or sample in machine learning. A column is a single property recorder for each example, often called a variable, predictor, or feature in machine learning. For example, the columns used for input to the model are referred to as input variables, and the column that contains the target to be predicted is referred to as an output variable. The rows used to train a model are referred to as the training dataset, and the rows used to evaluate the model are referred to as the test dataset. So we have two things here, input variables and an output variable. Let's go with input variables first. These are columns in the dataset provided to the model in order to make a prediction. And then we have this idea of an output variable. This is the column in the dataset to be predicted by the model. When you collect your data, you may have to transform it so it forms one large table. For example, if you have your data in a relational database, it's common to represent the entities as separate tables. This is referred to as a normal form, so that redundancy is minimized. In order to create one large table with one row per subject or entity that you want to use in your model, you're going to need to reverse the process and introduce redundancy in the data in a process referred to as denormalization. If your data is in a spreadsheet or database, it's standard practice to extract and save that to a CSV format. This is a standard representation that is portable, well understood, and it's ready to be used for predictive modeling processes with no external dependencies. All right, now that we are familiar with structured data, next, let's look at why we need to prepare that data before we can use it to model. Raw data must be prepared. We don't feed raw data to our machine learning models. Data collected from your domain is referred to as raw data, and is collected in the context of the problem you want to solve. This means you first must define what you want to predict, and then gather data that you think will help best make that prediction. This data collection exercise often requires a domain expert and may require iterations of collecting more data, both in terms of new rows of data that become available or new columns once identified as likely relevant to making predictions. So let's give a very vanilla definition of raw data. Raw data is data that's collected from your domain. In almost all cases, raw data will need to be changed before you can use it as the basis for your machine learning model. There are three main reasons why you must prepare your data for your machine learning project. Let's go ahead and discuss each of those. Number one, machine learning models or algorithms expect numbers. Even though your data is represented in one large table of rows and columns, the variables in the tables may have different data types. Some variables may be numeric, such as integers, floating point values, ranks, rates, percentages, and so on. Other variables may be names, categories, or labels represented with characters or words. And some may be binary, represented by a 0 and 1, which means true or false. The problem is, machine learning algorithms at their core operate on numeric data. They take the numbers as input and then predict a number as an output. All the data is seen as vectors and matrices, using the terminology from linear algebra. Therefore, raw data must be changed prior to training, evaluating, and using a machine learning model. Sometimes the change to the data can be managed internally by the machine learning algorithm. Most commonly, this is handled by the machine learning practitioner prior to modeling of what is commonly referred to as data preparation or data preprocessing. Number two, machine learning algorithms have requirements. Even if your raw data contains only numbers, some data preparation is still likely required. There are many different machine learning algorithms to choose from for given a predicting modeling project. You can't know which algorithm will be appropriate, let alone the most appropriate for your task. Therefore, it's a good practice to evaluate a suite of different candidate algorithms systematically and discover what works best on your data. The problem is that each algorithm has specific requirements or expectations with regard to the data. For example, some algorithms assume each input variable, and perhaps the target variable, to have specific probability distributions. This is often the case for linear machine learning models that expect each numeric input variable to have a Gaussian probability or distribution. That means if you have your input variables that are not Gaussian or nearly Gaussian, you're going to need to change them so they are Gaussian or more Gaussian. Alternatively, it may encourage you to reconfigure the model to have different expectations of the data. Therefore, there's a deep interplay between the data and the choice of model or algorithm you're going to use. Primarily, the algorithms impose expectations on the data, and adherence to these expectations requires the data to be appropriately prepared. Even if you prepare your data to meet expectations of each model, you may not get the best performance. Often, the performance of a machine learning model that have strong expectations degrades gracefully to the degree that the expectation is violated. The performance of a machine learning algorithm is only as good as the data you feed it. The old axiom, garbage in and garbage out, holds true in this space. Let's assume for a minute that we have sufficient data to capture the relationship between the input and output variables. A dataset may be a weak representation of the problem that we're trying to solve for many reasons. Although there are two main classes of reasons for this. It may be because the complex nonlinear relationships are compressed in the raw data that can be unpacked using data preparation techniques. It may also be because the data is not perfect, ranging from mild random fluctuations in the observations, referred to as statistical noise, to errors that result in out-of-range values or collecting data. We can think about getting the most out of our predictive modeling project in two ways. Number one, focus on the model and focus on the data. We can minimally prepare the raw data and begin modeling. This puts the onus on the model to tease out the relationships in the data and learn the mapping functions from the inputs to outputs as best it can. This is not the recommended approach. Secondly, we could push the onus back on the data or the data preparation process. This requires that each row of data best express the information content of the data for modeling. Just like denormalization of data in the relational database, two rows and columns, data preparation can denormalize the complex structure inherent in each single observation. This is the most reasonable path, and it's the one I recommend to you as a machine learning engineer. If you've ever followed me on Quora or read anything I've written there, you'll know that I say this time and time again. Predictive modeling is mostly data preparation. 80 to 90% of my job is working with data. It's not modeling. Modeling data with machine learning algorithms has become routine. The vast majority of the common, popular, and widely used machine learning models are decades old. Linear regression is more than 100 years old. That is to say, most algorithms are well understood and well parameterized, and there are standard definitions and implementations available in open source software, like the scikit-learn machine learning library in Python. Although the algorithms are well understood operationally, most don't have satisfiable theories about why they work and how they map algorithms to problems. This is why each predicting modeling project is empirical rather than theoretical, requiring a process of systematic experimentation of the model on the data. Given that machine learning algorithms are routine for the most part, the one thing that changes from project to project is the data. If you've collected data for a classification or a regression predictive modeling problem, it may be the first time ever, in all of history, that this problem has been modeled. You're breaking new ground. Now, that's not to say the class of problems hasn't been tackled before. It probably has, and you can learn from what they found in the results that were published. But it is today with your specific collection of observations makes your predictive modeling problem unique. Therefore, the majority of your project is going to be spent on data. Gathering data, verifying data, cleansing data, visualizing data, transforming data, and so on. Your job as a machine learning engineer is how to best expose the learning models to the unknown underlying structure of your prediction problem. The path to get there is through data preparation. In order for you to do that as an effective machine learning practitioner, you must know the different types of data preparation to consider for a project. You must know the top few algorithms for each class of data preparation technique, and you must know when to use and how to configure the top preparation techniques. This is often hard-learned knowledge, as there are few resources dedicated to this topic. Instead, you must often scour literature for papers to get an idea what's available and how to use it. Thankfully, you have this course now as a baseline for learning data preparation for machine learning models. All right, let's talk about some common data preparation tasks. We can define data preparation as a transformation of raw data into a form that's more suitable for modeling. Nevertheless, there are steps in a predictive modeling project before and after data preparation. The process of applied machine learning consists of a sequence of steps, and we've talked about this earlier. They are define the problem, prepare the data, evaluate a model, and then finalize the model. However, in this course, we're concerned with that step 2, data preparation. And there are common or standard tasks that you may use or explore during the data preparation step in machine learning projects. The type of data preparation performed will depend on your data, as you might expect. Nevertheless, as you work through multiple predictive modeling projects, you'll see and require the same type of data preparation tasks again and again. These tasks include data cleansing, feature selection, data transforms, feature engineering, and dimensionality reduction. All right, let's start off with data cleaning. Data cleaning involves fixing systematic problems or errors in messy data. The most useful data cleaning involves deep domain expertise and can involve identifying and addressing specific observations that may be incorrect. There are many reasons that data may have incorrect values, such as mistyping, corruption, duplication, and so on. Domain expertise may allow obvious erroneous observations to be identified as they are different from what to be expected. For example, in a feature with a person's height of 200 feet, that's obvious an input error. Once messy, noisy, corrupt, or erroneous observations are identified, they can be addressed. This might involve removing a row or a column. Alternatively, it might involve replacing the observations with new values. Therefore, there are general data cleaning operations that can be performed. For example, using statistics to define data and identify outliers. Again, we're going to talk about these later in the course. Next, identifying columns that have the same value or no variance and removing them. Identifying duplicate rows in data and removing them. Marking empty values as missing. Immuting missing values using statistics or a learned model. Data cleaning is the operation that's typically performed first, prior to other data preparation observations. I've created a diagram to give you some insight into an overview of data cleaning operations. All right, now let's talk a little bit about feature selection. Feature selection refers to techniques for selecting a subset of input features that are most relevant to the target variable that's being predicted. This is important as irrelevant and redundant input variables can distract or mislead machine learning models, possibly resulting in lower predictive performance. Additionally, it's desirable to develop models only using the data that's required to make a prediction, i.e., favor the simplest possible performing model, the old Occam's razor approach. Feature selection techniques may be generally grouped into those that use a target variable, supervised, and those who do not, unsupervised. The supervised techniques can further be divided into models that automatically select features as part of the fitting model, intrinsic, and those that explicitly choose features that result in the best performing model, wrapper, and those that score each input feature and allow the subset to be selected, which is called a filter. On screen, I created a visual representation of this. Statistical methods, such as correlation, are popular for scoring input features. The features can then be ranked by scores and a subset with largest scores used as input for the model. The choice of the statistical measure depends on the data type and the input variables, and a review of the different statistical measures that can be used, and we'll talk about these later on in the course. Additionally, there are different common feature selection use cases you may encounter in a predictive modeling project. For example, categorical inputs for classification target variables, numerical inputs for a classification target variable, numerical inputs for regression target variables. When a mixture of input variable data types is present, different filter methods can be used. Alternatively, a wrapper method, such as the popular recursive feature elimination, can be used that is agnostic to the input variable type. We're going to explore RFE later in the course. The broader field of scoring the relative importance of input features is referred to as feature importance, and many model-based techniques exist whose outputs can be used to aid in interpreting the model, interpreting the dataset, or in selecting features for modeling. All right, next up, let's tackle data transforms. Data transforms are used to change the type or the distribution of the data variables. This is a large umbrella of different techniques and may be just easily applied to input and output variables. Recall that data may have one of a few types, such as numeric or categorical, with subtypes for each, such as integer, real value floating point values for numeric, and nominal, ordinal, or Boolean for categorical. Again, I've created a diagram to show this overview. We may wish to convert a numeric variable to an ordinal variable in a process called discretization. Alternatively, we may encode a categorical variable as integers or Boolean variables, required on most classification tasks. We have discretization transforms. These encode a numeric variable as an ordinal variable. We have ordinal transforms. These encode a categorical variable into an integer variable. And then we have one-hot transforms. These encode a categorical variable into a binary variable. For real-valued numeric variables, the way they are represented in a computer means there is dramatically more resolution in a range of 0 to 1 than in a broader range of that data type. Therefore, it may be desirable to scale variables to a range called normalization. If the data has a Gaussian probability distribution, it may be more useful to shift the data to a standard Gaussian with a mean of 0 and a standard deviation of 1. So we've got two approaches here. One's called normalization and the other is called standardization. So normalization is scaling a variable to a range of 0 to 1. And standardization is scaling a variable to a standard Gaussian distribution. Again, we're going to cover that in more detail later in the course. The probability distribution for numerical variables can be changed. For example, If the distribution is nearly Gaussian, but is skewed or is shifted, it can be made more Gaussian using power transformations. Alternatively, quantile transformations can be used to force probability distributions, such as uniform or Gaussian, on a variable with an unusual natural distribution. An important consideration with data transforms is that the operations are generally performed separately for each variable. Therefore, we may want to perform different operations on different variable types. We may also want to use the transform into new data in the future. This can be achieved by saving the transform objects to a file along with the final model trained on all available data. All right, now let's talk about feature engineering. I would like to point out that I have an entire course on feature engineering, so this is actually a very deep dive topic. Feature engineering refers to the process of creating new input variables from the available data. Engineering new features is highly specific to your data and your data types. Therefore, it often requires the collaboration of subject matter experts to help you identify new features that can be constructed from the data. This specialization makes it a challenging topic to generalize to general methods. Nevertheless, there are a few techniques that can be used, such as adding a Boolean flag variable for some state, adding a group of global summary statistics, such as a mean, adding new variables for each component of a compound variable, such as day-time. A popular approach drawn from statistics is to create copies of numerical input variables that have been changed with a simple mathematical operation, such as raising them to a power or multiplied with other input variables, referred to as polynomial features. The theme of feature engineering is to add a broader context to a single observation, or decompose a complex variable, both in an effort to provide a more straightforward perspective of the input data. I like to think of feature engineering as a type of data transform, although it would be just as reasonable to think of data transforms as a type of feature engineering. Lastly, let's talk about dimensionality reduction. The number of input features for a dataset may be considered the dimensionality of the data. For example, two input variables together can define a two-dimensional area where each row of data defines the point in that space. This idea can be scaled to any number of input variables to create a large, multidimensional hypervolume. The problem here is, the more dimensions you have, the more space there is, the more input variables, the more likely it is that the dataset represents a very sparse and likely unrepresentative sample of that space. This is referred to as the curse of dimensionality. This motivates feature selection, although an alternative to feature selection is to create a projection of the data into a lower dimensional space that still preserves the most important properties of that data. This is referred to generally as dimensionality reduction, and it provides an alternative to feature selection. We're going to cover this later in the course. However, unlike feature selection, the variables in the projected data are not directly related to the original input variables, making the projection difficult to interpret. The most common approach to dimensionality reduction is to use a matrix factorization technique. Two of these are called PCA, or Principal Component Analysis, and SVD, or Singular Value Decomposition. The main impact of these techniques is that they remove linear dependencies between the input variables, i.e. the correlated variables. Other approaches exist that discover a lower dimensionality reduction. For example, we might refer to these as model-based methods, such as linear discriminant analysis, and perhaps autoencoders. Sometimes manifold learning algorithms are also used, such as Cohen self-organizing maps and T-distributed stochastic neighbor embedding. I've created a graphic on screen to show you an overview of the dimensionality reduction techniques. Data preparation is a process of transforming raw data into a form that's appropriate for modeling. A naive approach to preparing data applies the transform on the entire dataset before evaluating the performance of the model. This results in a problem referred to as data leakage, where the knowledge of the holdout test set leaks into the dataset used to train the model. This can result in an incorrect estimate of the model performance when making predictions on new data. A careful application of data preparation techniques is required in order to avoid data leakage, such as train test split or k-fold cross-validation. In the upcoming lessons, you're going to discover how to avoid data leakage during data preparation when evaluating machine learning models.